I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine a camera lens so thin it weighs less than a snowflake, yet focuses light better than the most advanced glass optics ever made. From smartphones to space telescopes, flat lens technology is rewriting the rules of how we see the world. Literally. This revolution, driven by meta-optics and nanostructured materials, is transforming imaging, communications, and photonics in ways once thought impossible. The story begins long before nanotechnology. In 1821, Augustin Jean Fresnel revolutionized lighthouse optics by replacing thick glass lenses with concentric prismatic rings, focusing light far more efficiently. Fresnel's innovation reduced bulk while improving performance, laying the groundwork for the ultra-thin lenses we see today. But modern meta-optics goes much further. Instead of reshaping glass, today's flat lenses sculpt the very phase of light, using nanostructures smaller than the wavelength of light. Centuries of optical evolution are compressed into layers thinner than a human hair. Traditional lenses bend light through curvature, focusing it onto a sensor. But this approach has limitations. Multiple objects at different distances require separate focus. Light at the edges can blur, and correcting chromatic aberrations demand stacked lens systems, making cameras bulky, heavy, and complex. Fast lenses, like those with f1.4 apertures, can exceed 50 millimeters in thickness, impractical for compact devices like smartphones, drones, and endoscopes. Mechanical autofocus adds latency and power demands, creating further challenges. Meta-optics offers a bold new paradigm. Instead of relying on curved glass, metalenses use arrays of tiny nanostructures, pillars, fins, or antennas that manipulate light with extreme precision. Materials like titanium dioxide, graphene oxide, and 2D semiconductors such as molybdenum disulfide enable unprecedented control over phase, amplitude, and polarization of light. Achromatic metalenses can now focus red, green, and blue light onto the same point, eliminating the need for multi-lens stacks and bulky optical assemblies. Early metalenses used concentric rings of gold nano antennas to bend light artificially. Later designs employed alternating layers of silver and titanium dioxide, supporting backward wave propagation and negative refractive indices for broader functionality. These breakthroughs allow flat lenses to operate over wide angles and multiple wavelengths, opening applications in imaging, sensing, and communications. Graphene oxide has added a new dimension. By using laser-induced reduction, researchers can dynamically tune the refractive index, creating lenses that are 10 times thinner than traditional glass, while maintaining optical performance. Caltech engineers stacked millions of silicon nanoposts to build wide-angle, achromatic metalenses compatible with CMOS processes, enabling direct integration into sensors for smartphones, medical tools, and satellite cameras. Advances in 2D materials like hexagonal boron nitride and molybdenum disulfide have produced functional lenses as thin as 190 nanometers, challenging classical design rules. Biohybrid lenses, such as microlens arrays using glass-coated E. coli bacteria, suggest a future of cheap, self-assembling optical sensors. On the quantum frontier, metalenses are being designed to focus entangled photon pairs, paving the way for chip-based quantum communication. The applications are staggering. Smartphones are shedding multi-lens stacks. Samsung achieves 10x optical zoom in modules thinner than 5 millimeters. Apple uses metalenses for focus-free, depth-aware HDR photography. In medicine, ultrathin endoscopes and wearable imaging devices benefit from lightweight, high-resolution lenses. Defense systems use long-wave infrared lenses that are over 100 times lighter than conventional optics, reducing strain on soldiers and enabling longer operational endurance. CubeSats now carry flat lenses for space imaging, and AR/VR headsets project ultra-wide fields of view from lenses less than 5 millimeters thick. Early flat lenses faced hurdles, narrow band operation, and expensive manufacturing. Today, inverse design algorithms optimize nanostructures for broadband performance, while nano-imprint lithography allows scalable fabrication on 300mm wafers at 40% lower cost. Metalenses integrate directly with CMOS sensors, eliminating traditional assembly complexities and paving the way for mass adoption. Looking ahead, tunable meta-optics promise lenses with adjustable focal lengths using phase-change materials or liquid crystals. Biohybrid lenses may create self-assembling, environmentally responsive sensors. Quantum-compatible metalenses could revolutionize secure satellite communication. Federico Capasso of Harvard calls them the integrated circuits of photonics, shrinking centuries of optics into chip-scale devices. The commercial impact is already visible. Metalens shipped over 20 million units in 2024, mainly for smartphone biometrics, and the broader meta-optics market is projected to hit $3 billion by 2026. Achromatic metalenses now cost less than 50 cents per unit, a fraction of traditional multi-lens assemblies. The transition from curved optics to flat lenses is one of the most profound shifts in optical engineering, opening new possibilities in imaging, sensing, communications, and even quantum technologies. We're entering a decade where every photon manipulated on Earth or in orbit might first pass through a metasurface. Flat lenses are not just about reducing weight or size, they're about coding light itself. The revolution isn't just here, it's shaping the way we see and interact with the world. Thanks for watching. Subscribe, follow, or visit IDSTH.com for more cutting-edge defense and tech insights. See you in the next one.